Welcome everybody to today's meeting, and welcome Leah, welcome Duncan, today's speaker. So today's speaker is Duncan Gilbert. He's a researcher at L'Occitane and Provence, and he's going to talk about so the title of his talk is From Particle Contact to Factory Floors, the Rough Journey of Non-Brownian Suspensions from Theory to Applications. So Duncan, please, introduce yourself quickly, and if you want to show your slides, please go ahead and tell us a bit about yourself. What's your career? What did you do? What are the studies you've done?
Okay, so I just prepped a slide just for that. So let's begin with it. So here is a bit of context. So here is a bit of my story. I graduated from, you're here. I graduated from ESPCI in 2018. Which is a French engineering school at Paris. Then I did my PhD with Elisabeth Lemaire in Nice, in both l'Université Côte d'Azur and les Mines de Paris, on a specific topic about the rheology of non-Brownian suspension, and more specifically about the impact of elasticity of the particles inside the rheology. Then I chose to go directly in not an academic position, but in industry. So I started a position as a research fellow at Capsum, which is a French cosmetic company. More specifically, they work on the macrofluidic way to manufacture some kind of products that are beautiful, and they sell it to Chanel, Dior, and all the big companies. And then after 10 months, roughly, I studied a new position as a research fellow also at L'Occitane en Provence. And 10 months after that, I was promoted as my actual job, which is a lead scientist also at L'Occitane en Provence. So
Nice.
it is a bit of my story, I guess.
And just a bit of a personal question here, because that's also what the participants in our webinars usually ask. First, how was the transition from a very fundamental research topic during your PhD to industry, and also, is it something you planned before the end of your PhD? Did you know you didn't want to stay in academia, or is it something you finally decided to do at the end of your PhD?
To be honest, I known before starting my PhD that I wanted to go to industry directly after that, to be honest. But I wanted very specifically to do a PhD because, first of all, I wanted to do research, even in industrial context. And in France, it's not that specific, but in international way, you need to have a PhD to do that. And also, I wanted to, in France, education is free. It's fully free, and I wanted to give back to France what they give me. So I really wanted to work for academic, just at least 3 years. And also, the transition was a bit rough, to be honest, because the difference is very high. Considering the time scaling, for example, it's 3 years for one project in thesis, but in industry, it's more like 3 weeks, probably more sometimes in research, for example, 6 months maximum, would say maybe 1 year, like for the big project. But actually the time dependency is more around the days, weeks, months, but not the years. But somehow it corresponds well to me because the thesis was good, but working on the same subject for 3 years, it was kind of rough for me, but that's kind of okay. And the transition was interesting because for sure in industry, you don't have the same academic levels than in academia, but they have empiricism that is very, very good. And what is very interesting for me is to make a parallel between the empirism and the reality of the theory in physical chemistry, especially. And that's very interesting for sure.
Well, you seem very happy about your job, and I'm very happy. As a consequence, I'm very happy for you too.
Thank you, my friend.
Well, with that, I think we can start. And people, the best way, is to answer questions as they come to your mind. So please raise your hand if you have questions, and feel free to interrupt the talk. Maybe Duncan, if you do some breaks during your slides, it would be great to give people the time to gather the questions. And that being said, please go ahead with your presentation, and thank you again.
Okay, thank you. I will come back to the presentation title. Okay, so to be honest, the presentation title was chosen by ChatGPT. So because I think that it's kind of good to do that, and so I just asked to have a funny title, and he wrote me this and a lot of other proposition. So I will try to talk both of what I did, just a little part of what I did during my PhD, and more specifically about what I published with Elisabeth Lemaire. And also, then I will just try to tell you a bit of a story of what I do right now and how I apply what I learned to my actual job. So the summary is I will begin with some introduction and context about academia and academic part and theory. Then I will talk about the impact of particle elasticity on rheology of non-Brownian suspension. And after that, I will tell you about another context, which is the industrial one. And then I will tell you a short story of industrial issue that I had like 1 year ago. Okay, which apply like perfectly for for biology. So here is a bit of introduction. So I just switch this one, and here is the team. Here is the team I work with. So here is me. I am a lead scientist in physical chemistry and artificial intelligence. I work with Nikita Lange, who is my research fellow, working with me on a lot of subjects and actually on all my subjects. And also, I have the chance to work with Daniel Sierra, who is a trainee for 6 months with me, working on AI and applicates AI directly on industrial topic. So let's begin with the impact of particle elasticity on rheology of non-Brownian suspension. There is a lot of difficult words, so let's take them one after the other. So what is a suspension? To be honest, we need to begin with some example. So here is 4 examples of suspension: 2 spades, concrete, blood, and also some fuel, some rocket fuel, more specifically the propergol. So there is a lot of different possibility to be a suspension, but what they have all in common is if you zoom directly inside, you can see something like that. So here is a video took by Frédéric Blanc in Nice. So it's exactly what you see when you look inside the suspension. It's a lot of particles that are moving each other inside the suspending fluid. So it provokes the fact that there is 2 big properties. First, the quantity of particle versus the quantity of fluid, which is called the volume fraction. And the other property is the viscosity of the suspending fluid itself. Okay? Taking that into account, we can go to the other big complicated word, which is non-Brownian. So what we call non-Brownian is the fact that if you measure the adimensional number, which is the Peclet number, which compares the convection and the Brownian thermal energy, it happens that it's 10 power 7, which means that the convection wins a lot in front of the Brownian motion, which also means a very specific thing is that there is no Brownian time, characteristic time inside the suspension. And in most of the cases, there is no characteristic time at all, which means that sometimes it's not necessary to sweep the shear rate, but it's more pertinent to sweep the stress actually. And that is a very important conclusion. Also, you can look at the Reynolds number, which compare the inertia versus the viscosity. And what happened is that the viscosity win a lot in front of inertia, which means that if you stop shearing, nothing happened anymore. I mean, if you stop pushing on your suspension, nothing happened. and nothing move. So there is no inertia. Okay, now let's talk a bit about the tribology part. Okay, so when you make in contact two particles, the surface contact deform and change the shape, and depending on the Young modulus of the particles. For example, if you take the two spherical particles as the example here, if the Young modulus is very high, like for glass or for wood or for rough materials, hard materials, the surface will not deform at all, or at least a bit. But if the Young modulus is super low, like for sometimes for some kind of hydrogel, for example, it will deform a lot, and which means that you can, using the Hertz theory, which take into account the elasticity of the particles for contact and the deformation, you can expect to measure the radius of contacts of your contacts depending on the normal force that you apply. Okay, and it depends on the Young modulus, as you can see here, and on the normal force for sure. Then let's dive into two very specific kind of contact: the adhesive one and the frictional one. For the adhesive one, there is a very important thing. It's that easily you can have a mind experiment and just close two particles and push it to each other, and then they stick, and then you try to pull them to separate them, and what's happened is that there is a force that goes the opposite of yours, just to opposite to the separation. This force is called the adhesion force, and what is super important is that it's independent on the contact surface, which is not that obvious. I mean, in some way, it only depends on the radius of the particle itself, and in omega 1, 2, which is another, which is a parameter that take into account the materials itself. I mean, for two particles of PDMS, for example, omega 1, 2 is constant, and takes the value of the omega 1, 2 for the PDMS itself, and R is only the radius of the particles. This result comes from the big work of GKR. It's a GKR theory. It's a referential paper. It's a paper of reference for this this kind of contact. The other kind of contact is a frictional one. It happens when you also pull two particles to each other and you try to slide them. Okay, and there is a tangential force that goes against your slides, which is called the frictional force, and it's proportional to the normal one, and the coefficient of proportionality is called the friction coefficient. Okay, this friction coefficient can depend on the normal force and sometimes not, and that's what we are going to see after. Okay, now I have to tell you a bit about a story. More specifically, the presence of a solid contact in a non-Brownian suspension is not that obvious. It was discovered like very late in 2011, proven in 2011 and 2015, for example, with the Blanc and al work and the Pham and al work. And what is very important is to understand that this contact goes through roughness of the particle itself. Okay. Also, there is a very big numerical work from Stanley Gallier in 2014 that proves that there is a possibility of impact of the variation of friction coefficient through the viscosity. More specifically, if you increase the friction coefficient, it will increase the viscosity, especially in the case of a concentrated suspension, which means that if you have a high volume fraction, the impact of the friction will be higher than in a low volume fraction. And that's a very important result. So you have kind of two regimes. You have the hydrodynamic one below 0.3 of volume fraction, and upper than that, you have the frictional one, or the contact one. Let's not talk about only friction, it's contact one. Okay, so here comes the big thing. There is sometimes shear-thinning in non-Brownian suspension, which means that the viscosity can decrease regarding the stress or the shear rate, depending on what you want to look. And what is important here is that it goes from a plateau to another one through a certain amplitude, and this amplitude depends on the volume fraction. If the volume fraction is high, this amplitude can be high, and if the volume fraction is very low, this amplitude can be very low also. So let's have a mind experiment together. Let's take the stress of 1 Pascal, for example, okay? And for 1 Pascal, you measure the viscosity regarding to the volume fraction, okay? And what you can see is that slowly the viscosity increases with the volume fraction until a point where the viscosity diverges, goes to infinite, and you stop flowing at all. Okay, and so let's take this point, note it with the arrow right here, and let's say it's the jamming volume fraction for 1 Pascal. Let's do the same experiment for 100 Pascal, and what happens is that you can, applying 100 Pascal, you can put more particles before it stops flowing. Okay, and let's do that through all the stresses that you can sweep. Okay, and you do that by fitting your viscosity curve with, sorry for the French, you can go do that by fitting the viscosity curve with this model, for example, which is the Marron-Pierce model. It's just a simple model that's hollow to fit. Okay. After that, you have this function that was created. It's the volume fraction, the jamming volume fraction through the stress. Okay, so it's at every stress you have a maximum volume fraction that you can put before it stops flowing. Okay, at very low stress it's very low. At very high stress it's high. Okay, but also what is interesting is that you can reverse X and Y axis to create this new function, which is the yield stress, contraint here, I'm sorry for the brain, which is the yield stress through the volume fraction. And what is interesting is that both functions are inverse from each other. Okay, and now we can just use this curve for a quick example. So you can have this packing volume fraction through the stress, and let's have an example. Let's take this example volume fraction and this stress example. If the stress that you apply is upper than the example, it will flow, and if the stress that you apply is lower, it will not flow. It's that simple. Okay. Also, next, we need to take into account the fact that Châté et al. And Lobry et al. Seems to prove that there is a link between frictional contact and shear-thinning in non-Brownian suspension. More specifically, Lobry et al. Prove that this shear-thinning seems to be induced by the variation of friction coefficient. Okay, and they created a model that is called the Steve model that take into account the variation of friction coefficient to explain directly the shear thinning, and it seems to work perfectly. And after that, this team with the paper of Arshad et al. It's also the team of Elisabeth Lemaire. They use 3 parts. They use IFM measurement of the friction coefficient. They put it directly inside the Steve model that I was talking just before, and they use that to fit with their experimental work, and it worked perfectly, as you can see on the right picture. Okay, so they kind of prove that there is a link between shear thinning and variation of friction coefficient, and that you can take into account using some friction coefficient variation model. Now we need also to talk about the frictional, the adhesive contact. There is less work on adhesive contact, to be honest, in non-Brownian suspension specifically. But I can see 2 papers, one of Zhu et al. And one of Richards et al. From 1995 and 2020. They both proposed a model, a population model, one of aggregated, non-aggregated particles, and one of adhesive to frictional contact particles. frictional contact population. Both model explain that if you, for example, for Richard et al., if you are at very low stress, it's an only adhesive contact population. And then if you increase the stress, it will go from adhesive to frictional contact population. And it's the Richard's model on the right that we will use for the paper to fit some curve. Also, I have to talk about a very important part is that you need to measure experimentally the viscosity. You need to take into account the fact that in non-Brownian suspension, the size of the particle is very high. It's like 100 microns. So you need to take into account what we call the crystallization or the structuration. It was very well enlightened by the work of Enzo D'Ambrosio in his thesis. But you can see that if you very close to the gap, very close to the geometry, there is a structuration layer, some structuration layer of particles that crystallize, okay, and that roll from through its rather every layer roll, okay, and it decreases a lot the viscosity very locally. The impact is that if you choose a too low gap, this viscosity will not, the viscosity that you measure will not be that interesting. It will be way lower than the real viscosity. So you need to work with large gap. Also, what is very useful for suspension rheology is that you need to normalize the viscosity with the viscosity of the suspending fluids. And after that, you need also to take into account the fact that you are, in the case of the shear-thinning, so for sure you work in plate-plate geometry, so you need to take into account the shear-thinning, so you need to correct with the Munet-Rabinovich correction, and also the inertia, if necessary. Sometimes you need to correct the inertia. Okay, here is the beginning of the work of my thesis. So in the work that we published with Elisabeth and Rudy Valette. So first of all, we need to manufacture some particles, well-known and well-controlled particles to vary not only the radius if we want, but especially the Young modulus. So we created a microfluidic system to craft some particles of PDMS, especially two type of particles, the stiff one and the soft one. The stiff one have Young modulus of 15 megapascal, and the soft one have a Young modulus of 1.8 megapascal, which means that the ratio is about 10 of Young modulus. The suspending fluid was chosen as the span AT because he's first of all is very Newtonian through all the range of shear rate and stress also, and with a viscosity of 1.5 pascal second. And also because the properties, physicochemical, more especially chemical properties, are interesting because it will wet well PDMS. So we have now two different modulus system with identical omega 1,2, because remember I was talking about omega 1,2 as an intrinsic properties of the materials, and it's the same materials. It's PDMS, so omega 1,2 is kind of the same. So we did measure the viscosity of the suspension through a lot of range of volume fraction for both soft and stiff PDMS. And also we added some measurement of glass beads suspension, because we wanted to have a perfectly elastic but non-plastic model for and not a variable friction coefficient to be compared. And using that, we use the Marwan-Pierce model to fit and to fit and to obtain the jamming volume fraction through the stress. And here is what we obtain. So first of all, look at the glass beads curve, which vary not a lot, which means that it's not that shear-thinning. The system is not that shear-thinning, and it's what we was waiting. Also, we can look at the soft and the stiff PDMS, and what is interesting is that they both are very different. The stiff PDMS is has kind of a bigger jamming volume fraction, and the soft one has a lower one. And what is interesting is that using the Richards model that I was talking before, we was able to fit it to obtain three parameters. First is the sigma A, which is the characteristic adhesion stress. Then we fit also the first jamming volume fraction at very, very low stress, which is phi ALP for adhesion loose packing. It's where everything is adhesion and less and not the friction is not so important. So the adhesion is the most important thing. And in the opposite, you have the high stress jamming volume fraction, which is phi mu here. And it's the case where the regime is purely frictional. First of all, we need to understand that an important result is that sigma A is in accordance to the GKR theory, because sigma A only depends on omega 1, 2, which is the same for both particles, and of R, the radius of the particles, but the radii of the particles are both the same. So sigma A should be the same, and it's what's happened. Also, we need to talk about the difference between phi ALP and phi mu, because they are quite different in both cases. So let's focus on the adhesive regime, so phi ALP. So what we learn is that, okay, sigma A should be constant and should be the same, and it's the case, so perfect. Now let's talk a bit about phi ALP. It's quite complicated because in this regime, you need to take into account both friction and adhesion, and also in this case, it's not only normal force adhesion, it's also the fact that it constrains the rolling. So you have a kind of a rolling friction. So we took some papers from Sainte and Al that try to take into account in some simulation the fact that particles can't roll at all, and it happens that we find out that it's possible that phi ALP has that kind of measurement, 0.39 and 0.5, but it would be the case if the rolling friction would be like super high. So it's hard to explain only using that theory. Considering the frictional regime, which happened when the stress is super high comparing to the sigma A, it's kind of interesting because you can use the stiff model, the one from Lobrier al, and you can use phi m, which is the jamming volume fraction for the frictional parts, the purely frictional parts. So phi mu, sorry, I changed the name, but it's phi mu. And you can switch directly using stiff model, phi mu, directly to the mu induced by the model. Okay, and it's 1 for the soft PDMS, and it's 0.25 for the stiff one. Okay, and using mechanical theory, you can predict that the ratio of mu from soft to hard PDMS, to stiff PDMS, should be only depending on the ratio of the Young modulus. And what is interesting is that considering the ratio of Young modulus that we have here, we should have a ratio of mu around 4.1. And what is funny is like 1 divided by 0.25 is close to 4, actually. So it's kind of interesting to have the same, a big similarity. Also, directly using the measurement of the prediction of mu that you have and all the parameters that you have, which is the Poisson coefficient and the Young modulus and the stress, etc., etc., you can predict that it should be induced by a friction coefficient of 80 kilopascal, which is consistent with the PDMS literature. So at this point, we were happy about that that knowledge. And if you want to learn more about that, you can for sure read the papers that we published in 2022. Okay, so in conclusion for the academic parts, so you have the adhesion loose packing volume fraction that can be up to 0.2, which is super low. It's 0.2, close to 0.2, because it's the beginning of the percolation. And below that, you will have no contact between top on right and bottom left of your gap, which means that you cannot have any yield stress. So the deformability seems to exacerbate the adhesion. Also, we can conclude that sigma R does not depend on the Young modulus, but only on omega 1, 2 and R. That's what we find out actually, and it's corresponding to the GKR theory. Also, after that adhesion regime, you also can have what we call a frictional regime with or without shear-thinning, depending on where is your adhesion regime, because shear-thinning happens for a characteristic stress also, and if this characteristic stress is way below sigma R, for example, or is close to sigma R, you cannot see any shear-thinning induced by the friction. The big question here is, does understanding tribology leads to understanding rheology? And in the frictional case, for sure, it's true. It's kind of true, because we seem to know a lot of things about that, considering all the papers that was published on the subject. But considering the adhesive case, there is for sure a lack of knowledge about friction, adhesive contact. So it is difficult to say that tribology induced rheology knowledge, but it's in a good way. So, okay, that part was the hard one, okay? Now let's talk a bit about the reality of an industrial context, okay? And to be honest, it will be a bit easier, but and also a bit funnier, okay? So first of all, the harsh reality of the rheology in industrial context is that I don't know why, but there is both possibility. If there is a rheometer in the industry, it's either the abandoned big dune in the end of the lab, you know, or the same rheometer that everyone used to answer to every question. Okay, I don't know why there is no middle. It's either it is useless or it is the most useful tool in the world. Okay, so knowing that, I created some kind of corporate rheology question, which is if you have money, you buy a brand new rheometer, okay, and if you only have time, it will begin to be the abandoned big tooth in the lab, okay. And when you arrive in this company, you are like, oh, do you have a rheometer? Is this, oh, is this a big tooth there? Okay, you can have it, take it, I don't care, okay. But instead of time, if you use a happy weirdo, you will have the saint rheometer of the weirdo, which is that the best tool of the world. Everyone wants to use it. It's like, wow, the best tool in the world. Okay. And actually, what is very important to understand is that rheology is quite cool. It's quite powerful, but it doesn't answer every question, you know. It's not like it is the best tool in the world. It's just a tool that answers some question. It is complicated. It can give you something wrong. It can give you something true. If you don't understand what you do, it is quite hard to use, okay? And it is not user-friendly at all. It seems to, but it is not at all. Okay, so let's dive into the harsh reality of what rheology is in industrial context. And the reality is, here is the big dudes. It's the Brookfield. It's a consensus, at least in the cosmetic company. Okay, so it's the standard way to measure viscosity. So it's just a viscosimeter. Okay, and the standard measurement is a fixed temperature, sometimes 20, sometimes 25. Okay, and also you fix the rotation per minute. It's 1 or 10 or 100, depending on the company, the guy, I don't know. And also, you need to wisely choose the geometry, because there is a gap. You need to have a torque like higher than 10% of the maximal torque of the machine. It's like that. It's a way. Okay, this is the way. The problem is this big dude give you only 1 point, depending on the geometry for sure, but taking one geometry, it gives you 1 point because it gives you one shear rate. Okay, let's, for example, take this curve. Okay, it will give you this point at 2 second minus 1 of shear rates. Okay. So the conclusion is that you have only one point. You need to introduce your geometry inside your bulk, which means that you probably will destroy it, but we don't care. Let's say that we have a lot of bulk, which is true actually for industrial company. Okay, so you just destroy it and leave it like this. Okay, and also you always measure something, which is already true for the rheometer, but it means that whatever you are doing, you will have a measurement. Okay. Oopsie, here is a little problem. Let's have a look at this guy, which is a nitrogel, okay? And let's have a look at this viscosity curve, which is the curve of the guy. And okay, so the viscosity is constant through a large range of shear rates. And then at one point, it just decreases because you destroy everything, okay? And it's irreversible. So let's say that you have a measurement with the Brookfield at this point where there is an arrow, and the Brookfield shear rate is 2 seconds minus 1. The Brookfield measurement is 900 centipoise. Okay. Oh yes, actually, everyone talk in industry. They all talk about centipoise. I don't know why. The first guys that should have talked at centipoise. I don't know why, but everyone talk about that. And no Pascal second here. Sorry. So let's talk in centipoise. It's 900, and that's okay. You have 1 point. And then here is this other big dude, which is Ricinus oil. Okay. It's perfectly Newtonian through a large range of shear rates. And the Brookfield at 2 seconds minus 1 also give you 900 centipoise, which, to be fair, for a manufacturing guy, it's literally the same. He has only 1 point, so it's the same points. It's the same guy. You know, hydrogel and Ricinus, it's the same guys for the manufacturing guy. The problem is that if you shear too much the hydrogel, it will like die irreversibly. Okay, so here comes the short industrial story that I kind of spoil a bit, and I call it the scale-up blind spot. So first of all, let's go to the left. There is a guy, or more specifically, it's a girl because it's in cosmetics, and there is a lot of girl in cosmetics. So there is a girl that is crafting some hydrogel at a lab scale. So it's 1 to 3 kilogram. Okay. Then there is a scale-up team that go upper in volume to 3 to 300 kilogram. Okay. And then there is this guy in manufacturing that do like 1,000 to 10,000 kilograms of hydrogel. Okay. They all work together to do a perfect scale up. Okay. And let's talk a bit about shear-induced drainage. No, the shear rate induced by the drainage, okay? In the lab scale, it's 0.5 to 1 second minus 1. In the case of the scale-up team, it's 1 to 10 second minus 1, okay? But in the case of the manufacturing, it's 100 to 1,000 second minus 1, which is kind of parallel to the Pascal's to the stress, because it is 900 close to 1,000 centipoise. You know, remember. So okay, perfect. You have both the shear rate induced and the stress induced. Okay, and let's go dive inside. So here is what happened really. You have a 10 tons reactor, which is like the biggest that we have here actually. Okay, and you need to empty it. Okay, you empty it through this big pipe with a length of L and a radius of R. The geometry imposed parameter is the stress, the maximum stress, which is R times delta P, which is the hydrostatic pressure, okay, induced by the highness of the reactor, divided by 2L, 2 times the length of the pipe. Let's say that we have a non-Newtonian fluid to take into account everything. So if you want to have a Newtonian one, you can keep n as 1 and it's okay. Okay, so you have a non-Newtonian fluid that respects this equation. Okay, so for example, you can plot in log scale the flow rates for k equal 1 and n equal 0.5, which means that it's a shear-thinning fluids, and for values R. Okay, so you have the flow rates that vary through a large range of maximum stress. Perfect, nice. And what is interesting is that it's not the stress that is imposed in your case, it's more like delta P, because you cannot change the stress, you change the highness of it's imposed by the highness of your reactor. So you need more to plot that graph, which is the maximum stress induced versus the delta P. Okay, so let's say that at pressure at T equals 0, you have delta P equal, it's not true, but have 10 Pascal, okay, induced by the hydrostatic pressure. Depending on the radius, you can have a lot of different maximum stress, which is quite important because sometimes the stress destroys your gel, okay? And if you have too much stress, it will destroy your gel. And what is interesting is that the more you constrain your fluid by reducing the radius, the less pressure you have, which is kind of counterintuitive, you know. And what is interesting also is that by choosing a too high radius of pipe, you can destroy everything because it induces a too high stress. Also, remember that you are in industry. So what you want is to go quick. So you want to empty it quickly. So you want to empty it the most quickly possible way. This conclusion, so it's hollow here to choose wisely the size of your radius and depending on the limit of stress that you are okay to impose. It could be true, but it's not true here because it's true for a chemical linked gel. But in our case, it's in a hydrogel that I know well, and it's a physical gel. So it's not stress dependent because it's not chemical, it's physical, so it's time dependent, okay? So let's do exactly the same conclusion, but for shear rate. Okay, so we plot, as always, we plot the flow rate through the maximum shear rates. We also plot the maximum shear rate through delta P as before. Okay, perfect. And now what we know is that regarding of the radius, you can have multiple maximum shear rate induced. So there is an issue that you need to take into account is that the delta P is constant because it's depend only on the highness of your reactor, but the radius is variable, but the length also is variable, but it's limited because the length could be like 10 meter or 100 meter if you want, but your manufacturing team will not be happy to have a 100 meter pipe length, you know. So you have to talk with your team before, with your manufacturing team before, just to know the limits of the length that you need to use. So here is what we know right now. Let's say that the team say 1 meter length. So you have a delta P of 1, and you take everything into account. Okay, perfect. So now you have the maximum shear rate through the radius of your capillary, of your pipe. Okay, perfect. Now, how do you choose the maximum shear rate that you are okay to impose? It's where the rheology appears. Hop, you just need to take your curve, okay, and you know that the viscosity is a plateau through a large range of shear rate, and then it just destroy everything. So let's stop just before the plateau go down, and let's call that limit SR limit, okay, for shear rate limit. Perfect. In the left part, the gel is happy. In the right part, the gel is not happy at all. It's just destroyed, and it's irreversible, and ciao bye. Okay, perfect. Then you have your limited shear rate. Perfect. You plot it inside. Here is the red curve. And also, it gives you the optimized radius that you are able to apply without destroying everything. If you want, you can just shift it a bit left to be sure that you will not destroy everything. That could be a good way to do that. Also, what is interesting with that model is that you can just change the K and N depending on the fluid that you have. Also, L, you can change it depending on the patience of your factory team, because sometimes it's 1 meter, it's not every time, but sometimes it's 4 meter, it's okay, and 10 meter, not at all, but depending on your factory team, you can change it. Also, you need to change delta P because regarding of the highness of your reactor, it depends. Sometimes it's a 10 tons reactor, so it's like, I would say 6 meter, and sometimes it's like 700 kilograms, so it's like 2 meter of 1.5 meter. And also, you need to take into account the fact that at the beginning, you have 6 meter, for example, for 10 tons, you have 6 meter of formula inside. And the more you empty it, the less formula you have inside. So delta P decreases slowly. So what is interesting is that you can also take into account this to put pressure directly inside the reactor to compensate that losses of delta P. So what is interesting is that it's not just an example, it's what's happened in production right now for me, like 1 year ago. So here is what happened. I choose wisely my geometry, my pipe, and I ask them to use that, okay? And they wanted before emptying directly inside, they empty it inside Pelican. It's a very big plastic bag, okay, of 1 ton, so 1,000 kilogram, okay? And before emptying it inside that, they wanted to empty it directly in a bin, in a waste bin like this, the white one, just to see what happened. And what is funny, oh, you have some. Okay, and what you saw here is that what goes through the pipe go very quickly, and it was destroyed. It was not was not perfect, and I told them that it was because there is no pressure, so no hydrodynamic pressure, because it's not plugged to anything. It's just on the open air. So the fluid cannot fully full the pipe. So I told them that it was very important to plug it directly in the Pelican, because it will not be true at all. My calculation take into account the Pelican, not the open air. And they told me that it's okay for us, but it will 1,000 kilogram of formula is like 3,000 euros. So it's a kind of a risk, and the risk is not for the manufacturing team, you know, it's for me. So they told me, if you are able to take the risk, we are okay. So, and what happened is that I told them to go through, and I just wanted to see. And what happened, guess I'm not fired, because it worked perfectly. And God bless me. And it worked perfectly. And actually, it's one of the best way for me to apply rheology is to take into account a lot of little parameters and a lot of reality to apply like physical theory directly in the manufacturing plan. And as a conclusion, I would be happy to say that both academic and industrial company are very interesting. Was very interesting for me. And I would say that the big difference between both is that in one you have a lot of time and you have less money, and the other one you have no time but you have a lot of money. So you try to deal with it and you try to do some business. And I guess that's the only difference, but we all do science. And thank you for your attention. I just plotted here my contact, but I guess I'm not sure it will be useful for you, but here is my contact. And thank you very much for your attention. If you have some question, I will be happy to answer.
Thank you.
Thank you. Thank you. People in the chat are saying great story and laughing. I agree with them. And okay, moments, questions. If you have questions, please, you either write them in the chat or even better, just open your mic and ask them directly to Duncan. So wait, well, I have a short question. What was the main reason why it was not working with the open air? Like when you in the bucket?
It was because the hydrodynamic resistance was not high enough. I mean, it's like in microfluidics, it's the same thing. If you apply not as much too much pressure, it will not fully fill all the pipe. So the equation that we take into account before take into account all the resistance of the pipe, but in this case, it's only fill half of the pipe, so there is
Sure.
open air every time. So the pressure is the same at the top and at the bottom of your pipe. So it's not Bernoulli at all after that. You know, it's kind of Bernoulli theory.
Yeah, yeah, okay.
That's why. So, for example,
And so the bags were like in vacuum before.
yes, exactly.
Oh, okay, that's the point.
back
Okay.
is kind of vacuum. Oh yeah,
Okay.
I didn't plot the picture, but the back is only vacuum, and it's like it filled little by little, okay, by the fluid.
Okay.
There is a question in the chat. Yeah, Michel, go.
Oh, it's more, okay, so here is a question. Great talk, thank you. What is the minimum volume fraction of solids required for a suspension to become non-Brownian? Actually, it's not the volume fraction that provokes the non-Brownian. It's more like the size of the particles itself. If you are, the theory is like, if you are below 1 microns, you are you are Brownian, and you will feel the thermal fluctuation. And if you are upper than 1 micron, roughly, you will be not non-Brownian, which means that you will not fluctuate with the thermal fluctuation. So it's not about volume fraction, it's only about size of the particles.
And also here you have a second constraint, which is you don't want inertia. So it's the particles are big enough not to feel the thermodynamics, but not too big, so that you can neglect inertia. It's practically it's your slide. So you have practically infinite Peclet number. So that means big enough, but also Reynolds number very small. So ideally equal to 0. So not too big.
Not too big at all.
And nice. So I mean I'm very happy that you showed us today that you can definitely that you're directly applying your PhD knowledge to your job, and that's cool. I think that's also a question about lots of people are afraid, like, is it really useful when I'm studying during the PhD? Well, the answer is probably it depends on the company.
It depends on the company or not.
Yeah. So, but there are places where you can definitely do research, real nice research as you're doing.
Yes, it really depends a lot of the company. Yeah. I mean, for sure, you have the liberty to do that. It's only depend on yourself, actually. If you are okay enough to work by your own and to prove that science, I mean theory, can be useful for the company, you need just to prove it. At the beginning, it's quite hard because you need to prove, first of all, no one trusts you, actually, at the beginning. They are like, okay, nice guys, let's do empiricism, and you go do whatever you want, okay? And when you prove one thing, then the second one, then the third one, then a lot of things. They try to they just begin to understand you and to listen to you, like, oh, okay, what do you say, weirdo guy? It's directly like that. Really, like in every company that I did, it's really like that.
Okay. Any other questions?
Rahul?
Yeah, please go ahead.
Hi, Duncan. Thank you for a great talk. I just
Thank
have
you.
a quick question. So, while emptying a shear thinning fluid, like the delta P, that would keep decreasing, right? And when the shear rate like drops down, it would create a problem to flow the liquid, right? For a shear thinning fluid. The delta P is not constant for the tank.
Okay,
Right?
the delta P is not constant in the tank, because for sure you change the length of the size of fluid that you have inside, and let's consider that the top of the reactor is open. It's in open air, so you have hydrodynamic pressure that is applied, so it decreases slowly. So the maximum pressure that you can apply is when the tank is full. Okay, and let's say that it's 6 meter top. okay, 6 meter highness, okay. And what is interesting is that this pressure, when it's applied, it will induced stress, or whether a stress or shear rate, okay. And let's call that the maximum stress or maximum shear rate induced by this tank. And if your formula is sensitive to the stress or to the shear rate or both, you need to take into account this induced shear rate and this induced stress to limit it to the maximum possible and to the maximum acceptable shear rate and stress. That's why you need to take that into account.
Okay, got it. Thank you. Thank you, Duncan.
You're welcome.
Thank you, Raul, for your question. And well, if there are no more questions, I think we can stop here the recording.